Push an endurance runner hard enough, and the margin between an optimal training session and a damaging overtraining state practically vanishes. The exact biological tipping point before the body begins to break down is the first ventilatory threshold, or VT1. Beyond this line, athletes rapidly deplete their glycogen stores and trigger heavy, multi-day fatigue. Identifying this threshold requires a laboratory setting. Athletes must wear restrictive respiratory masks connected to metabolic carts that measure the ratio of oxygen inhaled to carbon dioxide exhaled. Without access to clinical metabolic carts and specialized staff, most runners must rely on generic heart rate formulas to estimate their capacity. Recently, researchers have shifted their focus away from tracking respiration in the lungs to analyze cardiovascular signals. Total beats per minute only tells part of the story. Heart rate variability tracks the specific millisecond level timing between those beats. Scientists use a mathematical index known as DFA-a1 to read these microfluctuations. This index measures the fractal correlation patterns within those beat-to-beat intervals. A standard consumer-grade Bluetooth chest strap tracking at 1000 Hz can capture this fractal data during an everyday run. By analyzing the heart's fractal rhythm, researchers can intercept a real-time signal of internal stress, entirely bypassing the need for a laboratory gas mask. This process relies on the ongoing tug-of-war between the sympathetic and parasympathetic branches of the autonomic nervous system. This graph plots DFA-a1 values. At rest, parasympathetic activity creates a 1.5 baseline, translating to a highly uniform heartbeat pattern. As intensity increases, the sympathetic system takes over. The plotted signal fractures, dropping into erratic shapes. Researchers track the moment this path crosses 0.75. To test this, researchers put 15 runners on treadmills who wore both the traditional respiratory mask and the consumer chest strap simultaneously for an incrementally harder ramp test. The 0.75 threshold aligned with the gas exchange VT1 measured by the mask. The chest strap matched the lab's precision, effectively bringing professional threshold tracking to any runner, provided they are recovered. The researchers then put those athletes through a follow-up test. After running to total exhaustion, the runners rested for 5 minutes and immediately started a second identical ramp test. This chart compares the two tests. In the second ramp, the DFA-a1 signal plunges to the 0.75 threshold much earlier, at lower running speeds. Yet oxygen uptake data collected by the masks remained identical. The lungs took in the same amount of oxygen. The early signal drop occurred because the autonomic nervous system was exhausted from the first run. This fatigue threw the sympathetic-parasympathetic balance out of alignment, lowering the data baseline before the second test even began. This confirmed that while the DFA-a1 metric accurately maps the aerobic threshold, that precision is specific to athletes in a fully recovered state. This shift in the threshold functions as a sensitive diagnostic tool. It measures organismic demand. This tracks total systemic fatigue across the nervous network, a state that often exists without muscle soreness or a high perceived effort. An athlete can monitor this by tracking the DFA-a1 signal during a light 10-minute warm-up run. If the value drops unusually fast during that basic jog, it diagnoses systemic fatigue lingering from previous workouts. With this data, an athlete can downgrade the intensity of their planned session before it even starts, preventing them from pushing an already exhausted nervous system into overtraining. By tracking these fractal patterns, the consumer chest strap provides a real-time window into both the runner's current limits and their actual physiological recovery.